Qualitative analysis. Qualitative analysis. Let us assume that in figure Vn1 minus Vn2 varies from minus infinity to plus infinity. If Vn1 is much more negative and Vn2 M1 is off, M2 is on, and ID2 is equals to ISS. Thus, V out 1 is equals to VDD and V out 2 is equals to VDD minus RDISS as V in 1 is brought closer to V in 2. M1 gradually turns on, drawing a fraction of ISS from RD1 and hence lowering out M and hence lowering V out 1. Since ID1 and ID2 is equal to ISS, the drain current of M2 decreases and V out 2 rises. As shown in figure A, for V in 1 equal to V in 2, we have V out 1 equal to V out 2 equal to VDD minus RDISS by 2 as V in 1 becomes more positive than V in 2. M1 carries a greater current than does M2 and V out drops below V out 2 and V out 1 drops below V out 2 for sufficiently large V in 1 minus V in 2. M1 hogs all of ISS, turning M2 off. As a result, V out 1 is equals to VDD minus RDISS and V out 2 is equals to VDD. Figure also plots V out 1 minus V out 2 versus V in 1 minus V in 2. Here you can see the figure input-output characteristics of a output differential pair. The foregoing analysis reveals two important attributes of the differential pair. First, the maximum and minimum levels at the output are well defined, VDD minus RDISS respectively, and independent of the input CM level. Second, the small signal gain, the slope of V out 1 minus V out 2 versus V in 1 minus V in 2 is maximum for V in 1 is equals to V in 2, gradually falling to 0 as mod V in 1 minus V in 2 increases. In other words, the circuit becomes more nonlinear as the input voltage swing increases. For V in 1 is equal to V in 2, we say the circuit is in equilibrium. Now let us consider the common mode behavior of the circuit. As mentioned earlier, the role of the tail current source is to suppress the effect of input CM level variations on the operation of M1 and M2 and the input and the output level. Does this mean that V in CM can assume arbitrarily low or high values? To answer this question, we set V in 1 is equals to V in 2 is equals to V in CM and vary V in CM from 0 to VDD. Figure A shows the circuit with ISS implemented by an NFET and FET. Note that the summary of the pair requires that V out 1 equal to V out 2. Here you can see the figures. A differential pair sensing an input common mode change. B equivalent circuit if M3 operates in deep triode region. C common mode input output characteristics. What happens if V in CM equal to 0? Since the gate potential of M1 and M2 is not more positive than their source potential, both devices are off, yielding ID3 equal to 0. This indicates that M3 is in deep triode region because VB is high enough to create an inversion layer in the transistor. with ID1 equal to ID2 equal to 0, the circuit is incapable of signal amplification, and Vout1 equal to Vout2 equal to VDD. Now suppose V in Cm becomes more positive, modeling M3 by a transistor as in figure B. We note that M1 and M2 are turned on if V in Cm greater than or equal to VTH. Beyond this point, ID1 and ID2 continue to increase and Vp also increases. Figure C. In a sense, M1 and M2 constitute a source follower, forcing Vp to track V in Cm. For sufficiently high V in Cm, the drain source voltage of M3 exceeds VGS3 minus VTH3, allowing the device to operate in saturation. The total current through M1 and M2 then remains constant. We conclude that for proper operation, V in Cm greater than or equal to VGS1 plus VGS3 minus VTH3. What happens if V and Cm rises? Further sense, Vout1 and Vout2 are relatively constant. We expect that M1 and M2 enter the triode region if V in Cm greater than Vout1 plus VTH equal to VDD minus VRD ISS by 2 plus VTH. This sets an upper limit on the input Cm level. This, in summary, the allowable value of V in Cm is bounded as follows: VGS1 plus VGS3 minus VTH3 less than or equal to V in Cm less than or equal to min VDD minus RD ISS by 2 plus VTH VDD. With our understanding of differential and common mode behavior of the differential pair, we can now answer another important question: how large can the output voltage swings of a differential pair be? As illustrated in figure, M1 and M2 to be saturated. Each output can go as high as VDD, but as low as approximately V in Cm minus VTH. In other words, the higher the input Cm level, the smaller the allowable output swings. For this reason, it is desirable to choose a relatively low V in Cm, but the preceding stage may not provide such a level easily. Here you can see the figure: maximum allowable cutout swings in a differential pair. An increasing trade-off exists in the circuit of figure between the maximum value of V in Cm and the differential gain, similar to a simple common source stage. Chapter 3. The gain of a differential pair is a function of the DC drop across the load resistors. Thus, if RDISS by 2 is large, V in Cm must remain close to the ground potential. Thank you.